Not sure whether anybody is coming, but we're not going to show the QR code anymore because I need to share with you guys my iPad. So I'm going to stop showing that. As usual, we're going to start. We're going to go back to the previous example. There was a question from, I think, Aiman. Okay. He asked if we select the reference state to be the, for example, 500, somewhere. Was this the problem was this the question that was asked by Aiman? If we use the other reference state instead of, not this one, isn't it, Aiman?
Yes, doctor.
Is this the equation?
Yes.
Okay. Okay, that case, for example, if you choose the reference state to be that temperature, but then you cannot use that temperature as a reference state because that is the unknown temperature.
I choose 500 degrees Celsius.
Okay, so you choose 500 degrees Celsius. Fine. That's what we did, isn't it? The same. We did this at 500.
And for the table, I didn't solve it using the table. I used delta H directly.
Okay, you use CP. This CP, isn't it? From
Yes.
from the appendix table B2.
Yes.
Yeah. So you solve it directly. Fine. That's very good. I haven't tried it, but somehow your calculator must be more sophisticated than mine. So you can get it directly. So I haven't tried it using my calculator, so it's good. It's good news. But for those who doesn't have that sophisticated calculator as Aiman, then I guess you guys have to do it by try and error. Okay. Sorry. Oh, somebody have a background noise going on. Okay, let's. I remember there was a question. There was a question. I think must be not this question. Previous question. I forgot what question was it. It must be this. Okay. In this question, our reference state. Where is our reference state? Our reference state is based on the the 20 degrees C. 20 degrees C. Where is 20 degrees C? Okay. Oh, this is the question. The question, so I think Iman asked this. What if we use the reference state to be 300 instead of 200? We're not going to use it as 200. We're not going to use 200 as the reference state. Instead, we use the 300, the outlet temperature. Not the inlet temperature, but the outlet temperature to be the reference state. The outlet condition to be the reference state. So if you do this, definitely when you do the integration, when you do this, then this will be the reverse, isn't it? It will be 300 at the bottom and the 200 at the top. So you will get a negative sign here. Same thing, once you get a negative sign, but when you put inside here, there's going to be a negative sign. But if you do the calculation, let's go back. Where is that negative sign? That's negative. Okay. So if you do the calculation, where is that? Okay, that's negative. And now this is not going to be 0. Wait, oh, hold on. Let me get myself correct here. I just got it wrong just now. If our reference state is 300, let's go back again, 300. If our reference state is 300, where is 0? Which one is 0? At the reference state, isn't it?
Yes.
Okay, so that is the outlet, right?
Yes.
Okay, so this one becomes 0.
And
this one becomes negative 12.07, isn't it?
And air will be 0.
A? We don't change A because A has nothing to do with okay. A is still as it is. We do not change A. Yeah? Because A, we get it from appendix B8. Okay? So the only thing that we change is this. If you want to use your reference state at the outlet, not at 300, not the inlet, but outlet. So what happened? If you choose the outlet, this one becomes 0. The outlet enthalpy becomes 0. The inlet enthalpy, there's a value, right? So when you do the calculation, now let me erase this because this is not the one that we're going to have. Okay, oh dear. Put in black. Undo that. Okay. This is no longer, oh, I should have used red. Okay, this is no longer that value because that is 0. Okay, that is 0. But for A is still the same. Now, the 0 over here becomes negative 12.07. Now, when negative with negative, this is negative, that is negative, it becomes positive. So your answer will also be the same, 12.9. You will get the same answer, regardless of whether you use the inlet as your reference state or your outlet as the reference state. You still get the same answer. Do check the calculation. We did before this yesterday. We used the inlet. Now, I did based on your question, your Iman's question, we decided to use the 300 as the outlet as the reference state. We decide to do we select the reference state to be the outlet. The only thing that changed is between the inlet enthalpy and the outlet enthalpy. This one becomes 0 because that is at the reference state, and the inlet has a value. So when you do the calculation, negative times by negative, you will get positive. There. Okay, this is no longer 0 because the outlet is the enthalpy that is having a 0 enthalpy. So you will still get the same answer, regardless of where you choose your reference state. Should it be inlet? Should it be outlet? You still get the same answer. Okay, is that clear, everybody? Guys? Hello?
Yes, of course.
Okay, because I thought I might be there's a lagging in my reception, in your reception. That's why I need somebody to respond. Okay, guys, that's done with that example. Now let's look at this example. This is one example from your textbook. You're going to find the rate in kilowatt. That is the heat. You have a liquid stream of methanol at its boiling point, having a flow rate of 1,500 grams per minute, and you're going to get it. The outlet will be vapor. Okay, let's go through it. You have an input of liquid stream of methanol at its boiling point, having a flow rate of 1,500 grams per minute. The outlet is going to be saturated methanol. So if we draw the diagram, going to have liquid methanol having a flow rate of 1,500 grams per minute of methanol, CH3OH. I hope that's the correct formula. That's liquid. Okay. Then you have the same flow rate because you have only one inlet, one outlet, gram per minute of methanol at the now is saturated vapor. Saturated. Here it says it's saturated. Yeah. Saturated vapor. The question is, what's the amount of heat that you need to put in order to have it at from liquid at its boiling point? This is at its boiling point. We don't know the boiling point, but it's mentioned that it is at its boiling point, and you're going to produce saturated vapor. If it's saturated vapor, automatically this will be the same boiling point. Okay, it's the same temperature. What's going on here is just a change of phase from liquid to vapor. So the question is, what is the amount of heat that you need to put in order to produce the saturated vapor at the same temperature, same boiling point? So now we need to take note of the boiling point. Let's go to our appendix. Find the boiling point of methanol. So we will look it up in table B1. I need to go to table B1. This is quite a long scroll up. There is only B3. For you guys, you can look it up using your own textbook. Okay, where is methanol? I think I just found it. That is methanol. Okay, so I'll scroll up a bit so that I will know where is my boiling point. Oh dear, cannot see where is the boiling point. Let's go at the very top here. Where is boiling point? That is boiling point in degree C, and this is the latent heat of vaporization. Whenever you change from liquid to vapor at its boiling point, That is your latent heat of vaporization. This is latent heat of vaporization. I hope you guys have come across this term before. Have you guys? Anybody? Have you come across latent heat of vaporization? Nobody? No? You haven't come across it yet?
Yes, but no.
Yes, but no. What do you mean by that?
Like we have come across to the concept, but not the calculation.
Okay, okay, good. You have come across the concept. The concept is what I want now. The calculation, we will do it next week. Yeah? So the latent heat of vaporization is all about the heat that is supplied in order to vaporize the liquid at its boiling
After
point.
we did this in thermodynamics.
Yeah, it's the same. Yeah, it's the same. It's at its boiling point. It occurs at the boiling point where you change the liquid to saturated vapor. So that is latent heat of vaporization. Same thing. Okay, now let me see. This is, I need to know where is the boiling point, what's the boiling point of methanol? The boiling point of methanol is this. Let me change the pointer. That's the boiling point of methanol. And this is the latent heat of methanol. Okay. So it's 64.7 is the degrees in degrees C. So go back to our example. That is, which I keep on doing this. 64.7 degrees C. That is 64.7 degrees C. From the data from table 1, B1, we know that the latent heat of vaporization of methanol, CH3OH, at 64.7 degrees C, that value is the, what value did we get just now? If I can look it back, 35.27. Yeah, 35.27. 35.27 kilojoules per mole. That is from appendix. Now we're going to check whether we're going to get the same answer. Okay, this is the question. That is per mole. Our flow rate is in minute. Okay, so how are we going to do this? How are you guys going to do this? You have enthalpy 1, enthalpy in. You have enthalpy 2, enthalpy out. I'm not going to use 1, I'm not going to use in. So you're going to calculate the amount of heat. So what you have to do is, first thing first, basis. This value you get from the table. We're not going to check on that. It's already confirmed. That's the same. That's the value that we get from the table. So the basis should be 1,500 gram per minute. But because the unit is in mole, we're going to change that to mole. So your N is equals to 1,500 gram per minute. Change that into mole. So the molecular weight of methanol, let's go back to our table. The molecular weight of methanol, if you look at this table, that is the molecular weight of methanol, is it? Is that the molecular weight? Yes, yeah. 32.04. So let's go back to that example. Molecular weight is 32, keep on doing that. 32.04 gram per mole. Right. So cancel the gram. Your molecular weight will be mole per minute. So if you do that calculation, what did I get? I get 46. Somebody give me the answer. Is it 46?
46.82.
82. Thank you. Thank you very much. Okay, that's the molecular weight. Okay, now the question asks for the amount of heat that you need to put in. So reference state. What is your reference state? Anybody? What is your reference state?
Inlet.
Inlet. Okay. Inlet. Inlet. So your inlet is methanol. What liquid?
Saturated liquid. Right?
Saturated liquid. Yes, saturated liquid. That means at the boiling point. TB 64.7. And the pressure must always be 1 atm. Must always be at 1 atm. Okay. So that is your reference state. So this becomes 0. So now the question is, what is this outlet value? How to get that? Anybody?
We do energy balance equation.
You do the equation, okay? It's an open system. Going to tell me how to do this because I want you guys to interact with me.
Of course, delta H plus
Okay.
E kinetic energy plus E potential energy
Okay.
equal to Q plus W shaft.
Okay. Thank you, Aiman.
Welcome to it.
Okay. So what need to be cancelled off? Drop off.
The kinetic energy and potential
Again. Anything else?
shaft work.
Shuffle. Yeah. Yeah. So now you have to give reasons why, but I'm not going to write it down. You all know what to do. So we end up with Q equals to change in potential in the enthalpies, the rate of enthalpy. So if we do our normal, because this is open system, is out. That's molar flow rate times by specific enthalpy minus in molar flow rate times by specific enthalpy. Now, what is H out, guys?
H out is the delta H for vaporization.
Latent heat of vaporization.
Yes.
That's it. Okay. Your delta H vaporization is equal to H out at the boiling point minus H in. That is your H in. This is always liquid, and the out is always saturated vapor. Your saturated liquid is H in. Your H out is saturated vapor. This is always the case for latent heat of vaporization. Normally, if you do thermodynamic, I'm not sure whether it's the same symbol, but if in heat transfer, you have this capital H minus small h. Do we do the same symbol for thermodynamic? Is it the same? Small h? Small h because that is for liquid. Capital H is because it's vapor. Do you do the same thing? Guys? No?
I don't think so.
Small h. Is it?
Yeah,
Is it
in thermodynamics, we were using the X bar to calculate heat vaporization.
HY?
Yeah, we had some tables.
Oh,
Yeah,
okay.
we
Okay,
use
okay. I thought I was talking about the symbol. This is capital, this is small h. I'm not sure whether it's in thermodynamic, is it have the same symbol, the nomenclature. Is it the same?
We had the small for specific.
Oh, okay, okay. Then I better not use this. You might get confused. So I better not use this. Okay, let's just leave it as it is now. Latent heat of vaporization is the outlet enthalpy minus the inlet enthalpy if your inlet is at as a saturated liquid and your outlet is at a saturated liquid. So this is the same value that you will get there. So your outlet enthalpy is going to be the same as the latent heat because you assume your reference state is the inlet. So your outlet enthalpy is the same as the latent heat. Okay, so now if we put in the values, because we have only stream, we take that out. H out minus H in. Okay, so our molar flow rate just now, we managed to get 46.82 mole per minute. Okay, and our H out, we have 35.
Doctor,
Yes.
is it for delta H will equal to H2 out minus Hn plus latent heat for vaporization? So we cancel delta H out minus delta Hn because there's no change in temperature. We'll end up with latent heat because latent heat isn't only for the outlet stream. Am I right?
Hold on. What did you just say just now? Repeat it, please. Repeat it again.
I mean delta H will equal to H out minus Hn plus latent heat.
Plus latent heat of vaporization.
Hmm.
Okay, let's look at this. Okay, your H in is the enthalpy of the liquid, right? Saturated liquid. Okay. Your H out is the enthalpy of saturated vapor. Okay. When you look at steam table, we did this example yesterday. When you convert liquid water to steam, remember we have one example. Did you remember that? Let me.
Yes, the hypothetical bath.
Yeah, the one with the this one, I think. This one. Okay, you have liquid water. And let me change that. Okay, you have liquid water going to saturated steam, right? You just take that value from the appendix, from the steam table. You got this also from the steam table, right?
So it's not the same.
Same. Yeah. So you will get it from the steam table. Okay. So the same thing apply here. Okay. Same thing apply here. Because we already have this value. In fact, okay, let me point out. Since you already mentioned that, let's go to the steam table. I wanted to point this out because that is important for you to understand what actually is latent heat when you look at your steam table. Where is our steam table? Appendix B. Okay, that's good enough. I have this table B6 over here. Okay, I'm going to use this highlighter. This is the enthalpy of the liquid. This is the enthalpy of the steam. Okay, just now my question, what I mentioned just now is latent heat of vaporization is equal to H of vapor saturated minus H of liquid saturated. This must be saturated. Saturated, that is how I'm going to write. Saturated vapor, saturated liquid. So if you look at these values that we have here, 2508.5 minus 15.8, will it be the same as that value over here? Will you get the same? Will it be 2492.6? Will that be it? Isn't it? Isn't it?
Yes.
Yeah. So that's all about this is actually, sorry, what am I doing? I need to use this. Okay. This is actually latent heat of vaporization. That is actually latent heat of vaporization. That's what I just said just now. You get the saturated value of your the enthalpy of the saturated vapor minus the enthalpy of the saturated liquid. You will get the latent heat of vaporization. Okay, is that clear?
Yes. Thank you, Dr. Chu.
Okay. So now let's go back to this. So now we're going to have provided guys, your latent heat here will be H out provided the whole thing is done at its boiling point. And your liquid must be saturated and your vapor must be saturated. Provided, that is the requirement in order to have your latent heat. Okay, so that's your latent heat. So now let's go back to the calculation. So we will put in the value. Just now we said 32.21 minus 0. And that is, the unit is kilojoules per mole. So cancel that off. That is going to be in kilojoules per, I need to change it to minute because we want it to be in kilowatt. 1 minute, 60 seconds. And that will give you your answer in kilowatt. So anybody, can you give me a value, please? What is your answer?
27.48.
Sorry?
27.48.
29?
27.
27. Point? 48?
48.
Thank you very much. Thank you very much. Okay. Now, any questions? Any questions? Actually, what you can do is you have, this is the molar flow rate times by the latent heat of vaporization. That is actually what you're doing. This is, let me use a different color. Okay, this is your molar flow rate. This value actually is your latent heat of vaporization. What I'm doing before is to tell you what actually is going on. Okay, latent heat of vaporization is always the out minus the in, the enthalpy of the outlet minus the enthalpy of the inlet, provided it is at its boiling point. It is saturated. So in this case, it is at its boiling point. So this is what you are doing now. You are actually calculating using this formula, which is the molar flow rate times by the latent heat of vaporization. That's what you're doing. Any questions? Guys, any questions? Anybody? Any questions?
No, doctor.
No, good. Okay, let's look at another example. That example was 841. Now we're going to look at 842. Again, with phase change, let's look at the question. 100 gram mole per hour, liquid and hexane, 25 degrees C, 7 bar. You vaporize it, that means you're going to get vapor at 300 degrees C at a constant pressure. So that means you're still having a pressure of 7 bar. This is 7 bar, still the same. Neglect the effect of pressure on enthalpy. Estimate the rate at which heat must be supplied. We're going to calculate the same thing, heat. Okay? So what we are going to do, going to draw first thing first, draw your diagram. You have 100 mole, gram mole is mole actually, of liquid hexane. So what's the CH? What is the C is 12 14, isn't it? Symbol for chemical of hexane. Is that correct, guys? We can check it up in B, appendix B1. Because nobody is responding to my question, we can check it up in appendix B1. Okay, so that's temperature. Sorry.
It's correct.
Thank you.
The formula.
Thank you, Sulaiman. Because I forgot all my all these chemistry symbols, trying to remember what's the symbol. That's 300, 7 bar. Same. Okay. Now, you are asked to get the amount of heat for changing your hexane from liquid to vapor. Somebody tell me what to do, step by step. First thing, what is the first step?
Choose basis.
Basis. Okay, what is your basis?
100 mole per hour.
Okay, 100 mole per hour of liquid hexane. Fed. Okay. Next,
Choose reference state.
reference state. Okay, reference state. What is your reference state?
45 degrees C, 7 bar.
Okay, please write down your component. What is component?
Liquid hexane.
Okay, liquid hexane. So let's liquid. You can do it. You can write the whole thing, or what you can do is give the symbol for hexane, liquid, and 25 degrees C and 7 bar. You can write it as that. Okay. Yeah. Next.
Next, write out the first law of thermodynamics for open system.
Sorry.
The first law of thermodynamics.
Energy equation.
Write down the general equation.
Yes.
Okay. General equation is an open system. Okay, it's an open system. Give me the equation.
Del H
Okay.
plus KE
Kinetic
kinetic
Okay.
plus potential
Okay.
equals heating plus work.
Okay. Thank you. Heat plus work. Shaft work. Okay. Anything that need to be dropped off?
Kinetic
Anything.
and shaft work.
Shaft work.
And as well, potential.
Thank you, Sulaiman. Okay. Now the question asks for heat, and as always, normally you will get is a difference of enthalpy, and expand that out. We have molar flow rate specific minus in molar flow rate specific. Okay. Your molar flow rate is the same since there's only one inlet, one outlet. So that's take it out of the bracket. So H out minus H in. Okay, that is the equation to solve the heat input. for this process. Next, what are we going to do? Can you find the H in? Can you get it from the data? Or if there's no data, what to do? What is H in?
I think use temperature table.
H in is 0.
Sorry?
0.
0. Okay, I must say H in is 0. H out?
We have to find out. It's not.
Okay. Somebody just now said temperature table. What temperature table? Yes. What temperature table?
From Appendix B.
From Appendix B. What B? Table what?
B5, B5.
B5. Let's go back to Appendix B5. This is B6, B5. B5 has nothing to do with hexane. It's all about water, steam, that's all.
Oh, this is hexane.
Yeah, it's hexane. Let's go back. It's liquid hexane. Vapor hexane and liquid hexane. Stop.
But then we have to use latent heat and specific heat.
Okay. So let's look at the latent heat of hexane because we are changing it from liquid to vapor. Okay, let's go to the appendix. You will get that information in Appendix B1. We'll scroll up until we get table B1. Where is it? Okay, we need hexane. Okay, now where is hexane? All right, we just got it. Okay, there is hexane. This is hexane. That's the formula. What is the boiling point? That's the problem. I need to scroll up in order to know where is the boiling point. Okay, this is the boiling point. That is the boiling point, and this is the latent heat. So we take note of that. The boiling point is 68.74. So I'm going to go back to the question.
Doctor,
Yes,
the boiling point at what pressure we have to see?
because the boiling point is always at 1 atm. Oops, I got the wrong. Okay. The boiling point is always at 1 atm. It's always. And it's anyway.
Doctor,
But the question is 7 and 8 bar.
Yeah, the boiling point is at 1 atm. The question is at 1 bar. Yes. And
shouldn't we do a hypothetical path?
So you suggest hypothetical path. So let's do that. The boiling point is always at 1 atm. So we're going to have 1 atm is, if you write it down, is equals to 1.01325 bar. Yes?
We are changing the phase, then why the temperature isn't constant? Because in the TV diagram, it should have to be constant temperature.
The change of phase always occur at the boiling point.
Yes.
Okay. But the problem is the boiling point is at 1 atm.
Okay, but why the temperature change?
So,
Shouldn't be the same.
so that means we take the pressure at the boiling point, right? Which is 1 atm.
Yes. Oh, somebody is having a 2 lecture at the same time? You're having it simultaneously? Wow. Fantastic. You can do that because it's online. Okay. Go ahead. No problem. I have no problem. If you can concentrate both lectures at the same time. Okay, this is the boiling point. T boiling at 1 atm or 1.01325 bar. Yeah, and that is the latent heat for that vaporization at that temperature. So take note of that. We're going to go back to our example. What again? I have just forgot it. I just forgot. It is 68.74. Okay. 68.74.
Doctor,
Yes,
in the question, the pressure is 7 bar.
I know. So that's what we need to bear in mind. Okay, so now take note of this first. T boiling at 1 atm, 1.01325 bar. Somebody give me the value just now, 68.74, isn't it?
7.4, yes.
Is that correct?
Yes.
Okay, and the latent heat for that corresponding change of state is equals to
28.85.
85. So the unit is kilojoules per mole. Okay, so check whether the unit is actually kilojoules per mole. You need to check. Okay, latent heat.
Yes, it is.
It is. Okay, that is latent heat at that temperature. And where is the unit? Somebody?
At the top of the.
At the top, okay, at the very
No,
top.
I mean,
Yeah,
here is.
yeah. Okay, let's go back. 84 point, okay, this is the example. But the problem is this is at 1 bar. And this is the boiling point. That is the latent heat at the boiling point and at 1 bar. Our question is not at 1 bar. Our question is at 7 bar.
Doctor,
Yes.
I think for the first step, we go from 25 degrees centigrade and 7 bar to 1 bar.
So actually, what are we doing?
We're gonna build hypothetical path.
Thank you. We're going to construct ourselves the hypothetical path. So the first condition is 25 degrees C, liquid.
7.
Hold on, let's write down is liquid, 7 bar, 25 degrees C. Okay, that is your starting point. So you're going to change it to what?
Only the pressure to 1.1031.
Okay, change the pressure. Still liquid, still 25 degrees C, but 1.01325 bar. So you just change the pressure, delta P. Right, next.
Then we're gonna reach the boiling point.
Raise the boiling point to
Same liquid, same condition.
liquid. What is the boiling point?
68.74.
Okay, 68.74 degrees C, and we are still having the same pressure. So now we only change the temperature. Okay.
Yes.
After that,
We change the phase.
okay, now we're going to change it to vapor. What is the temperature?
Same.
Same, 68.74, which is the boiling point, and the same pressure. Okay, so when you are using that same, the information that we have so far, we will know that at that boiling point, at that 1.01325 bar, you will have this as the change. Sorry, I should be using it at the bottom. That will be delta H of vaporization. Okay, next, what to do? Because your final condition is not at the boiling point. The final condition is at 300. You are having a vapor at 300 degrees C and 7 bar. That is your final point. You need to go from your liquid to your final point. So, what next to do?
Change the temperature to 300 degrees C and same pressure.
Okay, same pressure, same vapor to 300 degrees C. You change the temperature, but same 1.01325 bar. Okay, now we are changing delta T. This one, we are changing delta phase. That is phase. Yeah, I give that symbol as phase. So next.
Then we're gonna reach 7 bar for the pressure.
Okay, finally we get to the bar. So that is delta P. That is your hypothetical path. So what actually you are doing, you are getting that value, outlet value. This is your inlet value. Your inlet value just now, you already specified as the inlet is the reference state. So your inlet enthalpy will be 0. So this overall enthalpy will be the sum of enthalpy 1, the difference of enthalpy 1, the difference of enthalpy 2, the difference of enthalpy 3, I'm going to give that is equal to latent heat of vaporization. This is enthalpy 4, and that is enthalpy 5. Okay, so the whole thing will be that the overall enthalpy will be the sum of all these enthalpies that we have in our hypothetical path. Delta H1 plus delta H2 plus delta H3 plus 4 and 5, lastly 5. Okay, now, which one will become 0? Delta H, what will become 0?
For 1 and 5 both.
1 and 5. I'm not sure about 1, but 5?
No, 5. 5 only.
Okay, because when you assume ideal gas, when you need to write your assumption, assume ideal gas. When you assume ideal gas will not be affected by change in pressure. It is mainly affected by change in temperature. So when it is independent of pressure, that will be 0. How do we know? Because we already look at the table when we did our hypothetical path last time. Let me go back to that table. We had this is at the okay. Where is it? At the very beginning of the note. At the very beginning of our note. There you go. Let me tidy this up. I better clean everything up so that you can see everything look better that way. Okay. Ideal gas. Change in pressure. Okay. Your delta H is the same as your delta internal energy. Change in internal energy and change in enthalpy is always 0. But when you're looking at liquid and gas, liquid and solid, it's not going to be 0. It's going to be the sum, the product of specific enthalpy vapor times by change in vapor. Okay, it's not going to be 0. When it's liquid, when it's solid, when you have a change in pressure, your enthalpy change will not be 0. Okay, so let's go back to that hypothetical path again. So this is not going to be 0. Ouch. What is it going to be? This is liquid. This is liquid. So what is it, guys?
V delta P.
Okay, specific volume times by change in pressure. Okay, but your specific volume is very small. Your specific volume is very small. Sometimes you can approximately become 0. You can assume it's approximately become 0, but we're not going to assume yet. We're going to calculate. Okay? So anything else that we need to put in value? Okay, this one, we can put in the value of our latent heat just now, 28.85 kilojoules per mole. Okay, what else? Change of temperature for the second step. What is the change of temperature for liquid? Go back to our table. Change of temperature. Sorry, I should not do that. I should be using this. Change of temperature at constant pressure. For liquid, that's the enthalpy. That's the change of temperature at constant pressure. The latent heat will be the sum of the specific volume times by pressure change plus the integration of Cp. So let's go back. Okay, that will be good. Keep on doing that. V delta P plus T1, T2, Cp dt. Okay, for this is gas. Let me tidy up. Please, I need to tidy up. This doesn't look good. Okay. dt equals to delta H2. Okay. So for delta H4, let's go back. This is about change in temperature, but we're looking at vapor. So if you look at the table for vapor, ideal gas, your equation will be that equation. That's the integration of Cp. Integration of Cp because it is ideal gas. So let's go back here. That will be, oh dear, I keep on doing that. T1, T2, Cp, dt. Okay. Your Cp will be for vapor. This Cp will be for liquid. There's two different Cp. Okay, next, what to do, guys? Delta H1. If we just look at the equation just now, specific volume, delta P. What's the answer? How to get it? Anybody? Anybody?
Should we assume that this is rigid tank?
Sorry, we assume what? Sorry?
That this is a rigid tank.
It's a rigid tank. No, because you have the inlet and outlet coming in. You can assume. Anything? Any suggestion?
I would use the standard.
Standard what?
The standard volume at like 22.4 STP as a conversion factor to change the volumetric flow rate of the methanol.
But you are not given anything in STTP, standard temperature pressure here. There's no mention at all about standard temperature pressure.
Okay, then I would use ideal gas law.
Ideal gas law. That is equal to what?
P specific volume V equal to RT. Then I solve for V equal to RT over P.
You said PV equals to nRT.
RT, no, yes, RT without M.
Okay.
Specific volume, specific, V specific.
Okay. Well, you can do that approximately, yes, for solid liquid, yes. But how about going back to appendix B1 and see whether we have any information that we can get from that appendix. Oops, not this, not this, not this. I'm looking at appendix. Okay. B1. Where is our compound just now? We were looking at what is the compound just now, guys?
Methanol.
Methanol. Okay. Hexane or is it methanol? Hexane, isn't it?
Hexane, yes. Sorry.
Hexane, okay. So, any information here that we can use?
The specific gravity.
Specific gravity. What Italy is that? What is Hg?
The mass over volume.
Mass or volume. You sure?
Gravity is the gravity of substance related to the water density.
Yes, and water cancelled because it's 1.
Oh, can you repeat that again? Sg is equals to?
The density of the substance related to the density of the water at 4 degrees C.
Okay. 4 degrees C. Okay, so that's what it says here, it's 4. Okay. So density of water at 4 degrees C is what?
1
1.
gram per centimeter cubic.
Okay, so that this equals to 1. 1 centimeter. How about using it in the same unit in kilogram per meter cubic kilogram? What is that value?
1,000.
1,000. Thank you. That's what I need. So therefore, the density is equal to Hg times by 1,000. That unit is going to be kilogram per meter cubic. We're going to use kilogram per meter cubic. Yeah. Is that right?
Yes, doctor.
Okay. So the density is going to be for methane C6H14 is equals to 0.659 times by 1,000, and that's going to be 659 kilogram per meter cubic. Yeah. Okay, so let's put that value. And what has it got to do with specific volume?
It's opposite the specific volume.
Okay.
1 over density.
Okay, 1 over density.
Yes.
Yeah? Okay, so put that value 1 over 659. Okay. 1 over 659 kilogram meter cubic. Okay, what else? Pressure change. For the H2, pressure change. No, so 1. Pressure change. What is the pressure change? Let me highlight 7 bar 1.10. Yeah, so the pressure change is 7 minus 1.0132.
1 minus.
Yeah, bar. Okay, now that doesn't look like having a unit of our usual unit kilojoules per, because we need the unit to be having the same unit as this, because we need to sum everything up, so it has to have the same unit. So how are we going to change that to the same unit?
Okay.
Isn't it P2 minus P1? 1.01 minus 7?
Okay, thank you. It should be the opposite, is it?
Yes.
1. Yeah, thank you very much. Somebody is very alert. So I'm going to erase that. It should be the other way around. It should be 2 out minus in, or final minus initial. So it's 1 point. Thank you very much. Thank you very much. Is that you, Aiman?
Yes, doctor.
Okay, good. So what else? What to do next?
Convert this to kilojoule per mole.
Okay, so how are we going to do? How to go about that?
M cube times bar is kilojoule, and but it's not exactly okay. M cube times bar is almost 10 to the power 5 Newton times meter. I could cancel out the m cube and bar and kilogram. So I convert this into mole using the molecular weight of hexane.
Okay, change into mole. Okay, the molecular weight of our hexane just now. What is the molecular weight just now? It's 32, is it? Hexane. Sorry, this is not hex. This is hexane. What is the molecular weight just now of hexane? Let's go back and look at our appendix. Hexane, the molecular weight is actually not 32. It's 86.17. Okay, 86.17. So that's molecular weight. Okay, 86. Oh, come on. I keep on doing that. 86.47, is it? I really, I can't remember. Because I just look at it, it's not 17. 17. It's not 47, it's 17. Okay. That is kilogram. It should be the other way around, isn't it? It should be here. Kilogram per kilomole. You guys going to tell me what to do because you guys going to solve this problem yourself. Okay, next. We want it to be in mole, so change 1 kilomole to 10 power 3 mole. Yeah. Anything else? You got the mole, but you cannot get. You haven't get the kilojoule yet. Anything else?
All right, like m cube times bar is actually 10 to the power 5 Newton times meter, which is 1 joule. So
Yeah, use your conversion factor. 10 to the power of 5. Sorry, it should be at the bottom, at the denominator. 10 to the power of 5 bar equals to
bar times meter cube.
Sorry?
There was the other way around, like m cube times bar is 10 Newton, 10 to the power 5 n times meter.
Doctor, can we use the R constant?
Yes, I was waiting for that. It's far easier to use the gas constant. Okay, anything with bar. That's the bar, isn't it? That's the bar. Okay, cancel the bar using that. Okay, so I was waiting for that. That is far easier. 0.08314. Okay, I'm going to erase this. So 0.08314. What is the unit? Let's go back. The unit is bar, liter. Okay, liter, bar, mole, Kelvin. Now we cancel the bar. The liter we can change it. 10 power 3 liter, 1 meter cubic. Okay, we cancel the liter, cancel the meter cubic. Still nowhere close to kilojoules per mole.
Use another gas constant.
Use another gas constant that has kilojoules per mole. So
We have 8.314.
Yep. Okay. So 8314. 8.8314. That is it should be at the top, isn't it?
Yes.
At the numerator. It should be joules, mole, Kelvin. So I need to erase that. Okay.
It's 8.3.
Thank you. So cancel the mole, cancel the Kelvin. We have joules, but we need in kilojoules. So 10 power 3 joules, 1 kilojoules. So we will have our answer in, let's see, will it be in kilojoules per mole? Is that it? Okay, let's see. Cancel this 10 power 3 with that, 10.3. So anything else that need to be cancelled? You are using the gas constant you are using it as a conversion factor actually. You need 2 of it in order to get your unit in kilojoules per mole. You have this as your, where is your gas constant? That is your gas constant. Okay, that is your gas constant. This is also your gas constant. So you have 2 gas constant there. So what's the answer? Should be negative. Why? Because 1 minus 7 bar. Should be negative. Anybody?
I got negative 0.078, but I'm not sure really.
Okay, anybody else getting a different value?
78.
7,
Yes.
8. Yeah. Anybody getting a different value? I hope everybody is getting the same value. What happened to the rest? You guys? Are you attending the other lecture at the same time?
Same.
Same, thank you. Thank you. Okay, now that's the first part. Okay, the second part, the second step, we have to calculate this. Second step. So, take down that equation, jot down the equation, plus the integration. What is the temperature one?
25.
25, going to?
68.74.
Okay, that's T2. Okay, 25, 58.74 degrees C. Your heat capacity should be that of liquid because you're dealing with liquid. So look it up in appendix B2. Go to appendix B2 for hexane. This is complicated because you have to use the heat capacity from appendix 2 for hexane. You need the equation, polynomial equation. So is it liquid?
MPLE.
Is it liquid or is it gas? And hexane. Okay, that's the molecular weight. We know that. We are going to use the liquid form because we start from liquid. We're going to use the first equation, the form A plus B plus C plus D. Okay, the unit is degree C, and this is the A times 10 power of 3. A times 10 power of 3 is equal to 216.3. So let's go back. And I got to remember to do that. Okay. What is it just now?
216.3.
216.3 times 10 power negative 3 dt. Yeah, so if you do now for this part, for the first term, what is that value? You're having a change of temperature only. You are having it at the same pressure. So what is going to happen to that first term?
It's gonna be cancelled.
0. It's going to be 0. Not going to be cancelled. It's going to be 0 because your pressure change there's no pressure change. You are at the same pressure. Okay? You're at the same pressure. There's no pressure change. So now do the integration. What is the answer? In kilojoules per mole. Anybody?
9.46.
9.46. Anybody getting a different value? Okay, good. So that's our second change of enthalpy. Our third change of enthalpy we know is going to be the change of phase. We have the latent heat for that. So we're going to write that down. Okay, guys, we have the latent heat for the third change of enthalpy, 28.85 kilojoules per mole. Okay, our fourth change of enthalpy. Let's look at our hypothetical path. Our fourth change of enthalpy involves integrating the Cp of vapor for N-hexane. So we need to go back to our appendix for the vapor. Just now, I'm going to change this to a different color. Let's use purple. We are looking at gas. Still having the same form. Number 1, temperature, degree C. That's A times 10 power of 3. That's B times 10 power of 5. That's C times 10 power of 8. That's D times 10 power of 12. Okay, so we're going to use that. I'm going to go back. It's going to be quite some, I'm going to need you guys to help me here. From T1, what is T1?
68.74.
Okay, 68.74. We have the same unit just now, degree C, so don't have to change it to Kelvin. And the final T2,
300.
300. Okay, 300. Okay, now A times 10 to the power 3. I need you guys to help me here.
127.44.
0.4 times 10 power negative 3 plus
40.85 times 10 negative 5.
okay. T temperature. Next,
Negative 23.92 times 10 to the negative 8.
thank you. And lastly, your D,
57.66.
57.66. I don't have enough space. Okay, I'm sure I have enough space. 12 10 to the power of 3 dt, D temperature. Okay. Please integrate. Thank you very much for helping. Give me the answer in kilojoules per mole.
47.19.
Again, please, 40, I heard 47.9.
19.
Okay, 19. Okay. So thank you very much. Everybody getting the same answer? Sorry, that's 5. Yeah, that's 5. That's 5, is it? That's a H4, not 5. 1, 2, 3. What am I doing? What am I doing? It's 4 or 5? It's 4, isn't it?
Yes,
It's
5 is 0.
It's 4, it's 4, it's 4, 4, 4 is 4. Okay. Okay. 47.19, is it, guys? Clean that up. Okay, that's 4. Okay. Is it correct? Everybody get the same value? Everybody get the same value? 47.19? Everybody? Guys? Hello? Anybody?
Yes, doctor, yes. I got it.
You get the same. Thank you, Sulaiman. And this last term, this last step is 0. We already mentioned because it is an ideal gas. It's an ideal gas. We mentioned that a change of pressure will not affect an ideal gas. So that's 0. So okay, now the overall, oh dear, the overall change of enthalpy, if you go back to our hypothetical path, will be H out minus H in equals to delta H1 plus delta H2. This is very long because we have to do our hypothetical path for this system as we don't have any available data to look up, okay, for us to get the enthalpies. So we have to draw our own hypothetical path. So this we say is equals to 0 because it is at the reference state. So now all we have to do is jot down the values that we have. For delta H1 is 0 minus 0.078. Make sure the unit, they are all the same. H2 is equals to 9.46. H3, 28.85. Remember, we got that from the latent heat in appendix B1. H4, 47.19. And H5, 0. The change in enthalpy at step number 5. So altogether, when you sum it up, what is your answer? In kilojoules per mole. Anybody? This is the H overall. And it turned out to be 85.4, is it?
Yes.
Yeah, thank you. Because I could hardly, your line must be not that clear because cannot hear you that well. Okay, this is going to be H out. Okay, let's put that value in our diagram, 85.4. 85.4 kilojoules per mole. Okay, what do we need to do next? Guys?
Apply the general equation.
Well, we already applied that. We have here the general equation.
Then Q equal to H.
Yeah, we need to solve this. Yeah, so now 85, what is our mole? 100 mole per hour. And 85.4 minus our inlet enthalpy 0. That is in kilojoules per mole. So if you cancel that off, what is the answer? The answer is in kilowatt. So we need to change that into a second. 1 hour, 3,600 seconds. So, and you will get what?
2.372
2.372 kilowatts.
kilowatts.
Is it the same? Wow.
Yes.
Almost the same. It should be the same. This is 238. We got 2372. Okay. Not bad. Any question, guys? Why is this so complicated compared to what we have done so far? It's more complicated because you don't have any available data to look up. You don't have any enthalpies that you can refer to in the appendix. You need to start from scratch. You have to start using your hypothetical path in order to get your outlet enthalpy. In order to get this outlet enthalpy, you need to draw yourself your hypothetical path. You need to construct your hypothetical path, starting from the initial condition, which is your inlet condition. Any questions? Once you manage to get your outlet enthalpy, the procedure, the step is the same. You are using this equation to solve it. That's the same. Nothing changed. Any questions?
No, just confirmation. Do I have to use the constant R in that conversion? Or I can do it my way? Because I got the same answer, exactly the same, without having to use 2R.
Okay. You can use the conversion unit at the front of the textbook to cancel off the unit. Yes, you can. But it's far easier to me if you use a constant R.
I mean, everyone has to choose his own.
You can use both. Remember, we did this last time. We have something to do with, let's see, what did we do last time when in chapter 7? We did this conversion also. It's the same thing. Yeah, you can use the conversion in at the back of the textbook. No problem. Aiman. You can check. That is the same. The answer is the same.
Yes, I did because I calculated using the other way around, and the answer is exactly the same.
Good. Okay, that's Ibrahim. I thought it was Aiman. Okay, Ibrahim. Okay, since you get the same value, so it's okay. You can do that. You can use the conversion factor, factor from the front of the textbook. No problem. Got any other questions? Anybody? Who's the one that is in Medina? Who's the one in Medina? Are you around?
Me, Dr. Ayman.
Aiman, you are in Medina. Okay,
Yes, but right now I'm in Skudai.
Sorry?
Right now I'm in Skudai.
Oh, but I thought somebody is still in Medina. No. Somebody? You are already here in Skudai. But I thought somebody is still in Medina. Somebody is online. Nobody? In Saudi? Okay. So all of you are here. That's good news. Okay.
No, doctor. I'm outside of Malaysia, but I'm not in Saudi Arabia. I'm in UAE.
UAE, okay. You're Faisal. Okay, Faisal, you are in UAE. It's 5
Yes.
hours behind, isn't it?
4 hours.
4 hours. Okay, that make it worse. When we have our 8 o'clock class, you are 4
At 4 a.m. Yeah.
Okay, that's better than Saudi then. Saudi is 5 hours.
1 hour
Okay.
difference.
1 hour different. Okay,
Yeah.
you are in UAE. Okay, because I have one student also in Madinah right now. Not in this class. I know of one student. Whether you and whether Aiman know him. His name is Anas. Your senior,
Anas.
1 year
Anas,
senior.
yeah. He's from
Yeah.
Yemen also. He's our senior.
Yeah, he's in Madinah now, and he's having classes online. You know, wow. But it's a good thing that he's in Madinah because it's so nice there. Okay. Any questions? That's just personal. I'm just asking. So Faisal is in UAE. Okay, nice. I haven't been there. It would be nice to go there. Faisal,
Yes.
how do you like
Yeah.
UAE? You are actually
It's
Yemeni.
good. Yeah. Yeah, I'm from Yemen actually.
Okay. Okay. Most of you are Yemeni, isn't it? All of you?
No, not all of us.
Oh
Most
no,
of
I
us
know
are.
Sulaiman is not.
Me,
Not most of.
I'm Egyptian.
I'm an Egyptian. Yeah.
I'm Chadian.
Ayman is Egyptian.
Yes.
Who is the other one?
It's me, Chadian. I'm from Chad.
Yeah, I know. You're from Chad. You did mention that last time. Okay. You're Egyptian. Ayman is Egyptian. You are the same like Ahmed. Your senior, Ahmed.
I know.
Okay. Okay, guys. Any questions before we look at another example?
No.
No questions? Good. Okay. Today we're going to do another example. We just did example 842. Let's go to 844. We're not going to do 843 because this is related to what we've been looking at so far. Okay, let's look at this. This is a bit complicated because you have a mixture. You have a mixture equal molar. What does equal molar mean? Same what?
50-50.
0.5.
Okay, good. Thank you. You have a liquid mixture of equal molar, 0.5 mole of benzene and toluene. Somehow, the author, if you look at chemical engineering textbook, they like benzene and toluene a lot. I don't know why. Yeah, 10 degrees C, it's liquid. You're going to heat it up to 50 degrees C, from 10 to 50. Now, what happened is that you're going to produce two products, two streams coming out. One of it is going to be in the form of liquid, whereas the other stream is going to be in the form of vapor. Okay? The liquid stream is going to contain 40 moles percent benzene, whereas the product vapor is going to contain 68.4 mole benzene. You're just referring to benzene. You're not referring to toluene, but you know what to do. You only have two components, benzene and toluene. So if one of it is given, you can calculate the other value for toluene. So the question is, what is the amount of heat that need to be transferred per mole of feed? So your feed will be per mole. So first thing first, you need to draw the diagram. Okay, this is our block diagram. Coming in, you have liquid mixture. What is the amount? The amount should be 1 mole. I'm going to erase that. Oh, okay, 1 mole of feed is mentioned there. So you have 0.5 mole per mole of benzene. Let's B be benzene. 0.5 mole per mole of toluene. Okay, I'm going to give the temperature is given 10 degrees C. There's no mention at all about the pressure, so we're not going to write the pressure there. We're going to have two products coming out. The top product will be vapor. Give it the same symbol of V for vapor, and the bottom product will be liquid, NL. So that's going to be mole and mole. Your top product is vapor having a composition of 0.684 mole per mole of benzene, and your bottom product will have a composition of 0.4 mole per mole of benzene. So automatically you will deduct that to get the mole percent for toluene. And for this case, if you subtract, it should be 316 mole per mole of toluene. Okay. What is the temperature of it's heated to 50. So this is going to come out at 50 degrees C, and this is also going to be at 50 degrees C because both of them coming out from the same vessel. So both will be at the same temperature. The question is, what is the amount of heat that you're going to, there's no dot over there because there's no red. Because you're using just mole. So what is Q? That's the question. Okay. This is liquid coming in. This is vapor at the top, liquid is at the bottom. This is quite complicated because you have two components. First basis, 1 mole feed. Okay, 1 mole feed. So next, we're going to solve for Q. So we know we're going to use the equation for the open system. No dot on top because we are not looking at flow rate. We are just looking at the amount.
Doctor,
Yes.
should we do mass balance first?
Yes. Mass balance first. Because you don't know what is NV and L. Okay, so now that is your energy balance, mass material balance.
And for energy balance closed system, isn't it DELU?
It's not closed system, it's an open system. Why is it an open system? Because mass are coming and going out. Okay, so it's an open system. This is an open system. Okay, do the material balance. You need to find NL and NV, the top flow rate and the bottom flow rate. Okay, total balance. Total balance. What is the total balance? Look at the flow rate, the diagram. What is the total balance?
N1 equal NV plus NL.
Okay, thank you. 1 equals to NV plus NL. That's the first equation. Okay, that's the first equation. I'm going to have a benzene balance. Just benzene. Just benzene.
And the variable do we have?
Sorry, Ibrahim?
I said how many variables do we have? Two.
Yes.
Two.
You have two components, or you have two variables.
Yes.
So, what is the balance on benzene? Input equals to output. This is simple material balance. Input equals to output. So, what is the balance for input?
0.5.
Sorry?
0.5.
0.5. Okay, the mole fraction times by 1 of benzene is equals to the mole fraction for the top flow rate. The vapor?
0.684.
Okay. Thank you. 0.684 times by NV because that's the unknown. And the bottom flow rate, the mole fraction of benzene is 0.4 times by NL. Now you have two equations, two unknowns. From the first equation, you can get NV is equals to 1 minus NL. So substitute that inside here. So you can have only one, you are left with only one unknown, which is NL. So what is NL? It's in mole. Anybody? Let me look at my calculation.
0.5.
I got 0.648. Anybody get the same thing? Same value?
Yeah.
Good. So now you substitute that 0.648. Your NV is equals to, let me have a look at my solution, 0.352 mole. Okay, that's our value for the flow, for the amount of NL and NV. So I'm going to put that inside this diagram, 0.648 mole and NV 0.352 mole. Okay. Next, once you have get your material balance done, you need to solve for the Q using your energy balance. Drop the kinetic energy, potential energy, work shaft as always. Reason, you know what to do. So you end up with Q equals to change in enthalpy, and that is going to be, okay, let undo that, out and specific enthalpy minus in and molar, it's not molar flow rate, it's mole. So that's the equation. So now, what next? Reference state, guys. What is your reference state? What is your reference state? What? What reference state?
10 degree C, liquid mixture.
Okay, the inlet. Okay, let's choose the inlet. Okay, benzene liquid at the temperature 10 degrees C. We're going to assume it's going to be at 1 atm. We also have toluene liquid at 10 degrees C and 1 atm. So that is your reference state. Okay, so now We're going to construct ourselves our table as usual. We have benzene liquid, toluene liquid, going to have benzene vapor, and we're going to have toluene vapor. Yeah, our in flow rate mole, our enthalpy in kilojoules per mole. Quite a long solution for this problem. Out mole, and our H out specific out enthalpy kilojoules per mole. Okay. So the amount of benzene liquid coming in, we know is equimolar. 0.5 times by 1, 0.5 times by 1. This is the mole fraction. That's the molar flow rate. So it's going to be 0.5 when you multiply it up. So just put that value over here, 0.5, 0.5. There's no inlet vapor coming in. So that's no inlet vapor coming in. But the amount of mole coming out for both the vapor and the liquid is there. This is for vapor. So what is the amount of benzene over here? 0.684 times by 0.352. That is the amount of benzene. Mole benzene. Over here, your mole of toluene, 0.316 times 0.352. That equals to mole of toluene. If you multiply that out. Okay. And for here, your mole of benzene is 0.4 times 0.6848. That is your mole of benzene. Over here, 0.6 times 0.648. That's your mole of toluene. So give me the values. What is this? Anybody? 0.684 times 0. I'm using the mole fraction times by multiply with the number of mole. So what is that? For mole of benzene, anybody? Oh, nobody is responding. Okay, I do the calculation then. You guys are tired? Am I speaking alone? Am I alone now?
Yes, doctor. We're a little tired.
Tired. Okay, you little tired. Wow. Give it. Take 5 then. Take 5.
Okay, doctor.
Okay.
Thank you.
You're welcome.
Okay,
Take 5.
doctor.
Okay. Hey guys, welcome back. Hope you guys feel refreshed. Are you with me?
Yes, yes,
Yes,
doctor.
doctor.
Okay, I thought you're still taking a rest. Anyway, oh dear, need to get this. Hold on. Stop sharing first. Okay, let's stop sharing this first. Let me get my iPad so that we can continue with that example. Okay. Hope the internet is okay. Taking quite some time to upload. Okay. What I did just now, right? Now let me show you guys. What I did just now is I'll calculate the amount of benzene in that flow rate at the top. That's the amount of benzene, which is that amount. What I did is actually I get the total flow rate. The total flow rate is this, multiply with the corresponding mole fraction. So I will get that value. This is the value for the amount of benzene in the vapor phase. So I will write that down in our table 0.2408. Vapor phase for benzene 0.2408. That is the number of mole of vapor of benzene in the vapor phase. For the toluene, this is the amount after I have done the calculation, 0.1112. So I'm going to write down 0.1112. And for the liquid phase, I have over here, that's for the amount of benzene, 0.2592. And for the vapor phase, after I've done the calculation for, sorry, it's not the vapor, the liquid phase for toluene, 0.3888. 0.3888. Now, just now we said that our reference state is liquid benzene, liquid toluene at the inlet condition. So what is the enthalpy at the inlet condition for both components?
0, doctor.
Thank you. 0, 0. Now we have to calculate this value. Let's put it as 1. Enthalpy cap 2, specific enthalpy 3, specific enthalpy 4. Okay, let's look at liquid. Liquid is easier because normally the polynomial equation is shorter for liquid. So let's write down the enthalpy H1. How to get H1? How to get H1? It's liquid. You are initially at 10 degrees C. You're going to change to 50 degrees C. They are both liquid. This is liquid. This is also liquid. So how to do that?
Hypothetical bath.
Hypothetical, do you need that?
First look at the table. If we found it, that's perfect. If we do.
Okay.
Doctor, by integration?
Sorry?
By integration?
Integration. Yes, Omar, you got it right. Why are we not doing? Why are we not doing hypothetical path?
Constant pressure and the phase is the same.
Okay, that's right. The pressure we assume is the same at 1 atm. Okay, both the liquid and both liquids at the inlet and the liquid at the outlet is the same pressure. We are having both liquids, so there's no need to get the hypothetical path. It's just a heating up. It's just heating. We are just heating it up. There's no change of phase at all. So we don't need hypothetical path. So don't bother with the constructing hypothetical path. So now we're going to go from 10 degrees C. We're going from 10 degrees C, which is the inlet, to the final temperature that we want, which is 50 degrees C. We need to get the Cp of H1 is Cp of benzene liquid with respect to temperature. Okay, the same thing you do for toluene, which we denoted as H2. So the temperature will be from 10 degrees C to 50 degrees C. You'll be looking up the heat capacity of toluene, liquid toluene, with respect to temperature. So now let's look at the table B2. We need the appendix table B2. So this is B2. So we need toluene, and benzene. So let's look at benzene first. Okay, there is benzene. Okay, benzene over here. We have liquid benzene. We have the first equation, the form of a first equation. The form of the first equation is this. Okay, A, B, C, D. That's the temperature unit you're going to use. And that is A times 10 power 3. That is B times 10 to power 5. That is our benzene. So let's go back to the example. Let me try to write that down. 126.5. Make sure that I got it right. Minus 3 integration from 10 degrees C to 50 degrees C plus 23.4 times 10 power 5. I got it written down earlier because I have done it earlier. So what is the answer, guys? When I did it, I got 5.3408 kilojoules per mole. Did you guys also get the same value?
Yes, doctor.
Okay, good. So I just fill it up, 5.3408. Okay. For do the same thing for toluene, let's go back to our appendix. For toluene, it's going to be somewhere near to the bottom of the table. Okay, there it is. Okay, that's toluene. This is your liquid toluene. We're interested in liquid. We're not looking at vapor. The first form, the unit of temperature, 148.8, 32.4. Okay, just remember that. Then let's go back to our example. So if I write that down, from 10 degrees C to 50 degrees C, 148.8 times 10 to the power negative 3 plus 32.4 times 10 to the power negative 5 temperature with respect to temperature. So if we do the integration, what is the answer? After I've done it, I got 6.3408 kilojoules per mole. Anybody getting a different value?
The same, doctor.
Same, thank you. Okay, 6.3408. Next, H3. H3, we are looking at vapor. That's vapor. T is also vapor for temperature H4. So we need to do what for H3? There is, okay, let's look at the diagram. You are going from 10 degrees C to 50, no problem, same thing. But you are actually going from liquid to vapor.
Then the latent vaporization. Heat vaporization.
Okay, it involves latent heat or vaporization. So what do you have to do now? You need to look up what?
Look up the table, the latent heat.
Okay, latent heat.
Yes.
You need to look up the latent heat and also the boiling point temperature. Okay, for both benzene and toluene. So toluene, I just miss it. Where is toluene? Okay, there is. This is toluene. So our boiling point, that's boiling point, that is the latent heat. Okay, that's for toluene. Jot that down. You need that. Okay. And for benzene, we need to go further up, scroll up. Where is benzene? Okay, that's benzene. That is the boiling point, I think. Yep, that's the boiling point. That's the latent heat. Okay, you need to write that down. So we're going to go back to the previous example. We're going to write down that information. Where are we going to write it down? Maybe we should write it somewhere else. Let me erase this first. Okay, I need to write down for benzene, the T boiling. Anybody remember to jot it down? For benzene, it's 80.1, is it? Degree C. Did you write it down? Nobody? Latent heat of vaporization is equals to 30.765. Did somebody jot it down just now? Is this the same? Just as I wrote it now. T boiling of toluene is equal to 110.62 degrees C. I will go back and check. Okay. Vapor 33.47 degrees kilojoules per mole. Okay, let's look at top benzene. 80.1, the boiling point of benzene. 80.1. The latent heat, 30.765. Is it the same as how I wrote it down? 30.76, okay? So the same thing for toluene, that's the boiling point, and the latent heat. Okay? So what next? We are not boiling it at 80. We are not boiling both components at the boiling point. We are evaporating it at 50. So what to do? How to get the latent heat?
Then
How to get the enthalpy? H3 and H4. How to get it?
Use the hypothetical.
Yes, you have to do the hypothetical path.
Doctor, in this case, the pressure is high because if the boiling point, like it's not as the usual, then the pressure has to be higher than the usual, right?
The boiling point is higher than usual?
No, it's normal boiling point 80
Yes.
degrees C, and now it's 50. It's boiling at 50. Then the pressure is now is higher than the usual pressure. Right?
Yes, but we are not given the pressure, are we? Any
No.
mention of the pressure?
No.
No. So I'm assuming that it is at 1 atm. I'm assuming because there's no mention that.
But doctor,
And they
Hello?
yes, yes.
hello.
Yes, yes.
Yeah.